Hello everyone, welcome to another session. Today we're going to do some chemistry, specifically talking about unimolecular reactions, which are reactions of one molecule. But when we look into the details of how this physically happens in space, the molecule is not alone. It's actually a process where depending on the whole mixture, the concentration of all the molecules in the mixture determine how fast this change of one molecule happens. So this unimolecular reaction it's one species, one molecule changing or breaking down So it's called unimolecular because only one thing changes. But actually, it's not alone. Actually, a third body or second body. It's called third body because it doesn't matter what it is. It's anything in the mixture that can collide with it. The actual chemistry is not the mechanism. It's just the collision partner. Anything in the mix that it can collide with. A third body, M, is also involved. So it's a unimolecular reaction because only one thing changes. But you need this third body, another collision partner, to get things going. Okay, so what we mean by this unimolecular is we have this species A, and then what you see, the global simplified process, if you were going to describe it in one step, would be that some unimolecular thing happens where all of a sudden this A just changes. So that's the global summary of what happens. But the mechanism that this goes by is a set of elementary steps, of course. Mechanism for unimolecular process. So it's a unimolecular process in terms of the global mechanism, the global description, but the elementary steps are not only involving one species. It's actually a three-step process. That's the three fundamental steps that can be used to get some feel for what's happening. So if we define this forward step, where we're starting off with this single molecule that we see, and it's going to change. What actually happens is the first step to get this going is with the third body in the mixture. This can be anything. So third body is, we'll talk about that. This is the third body. It's anything in the mixture. I've been saying this verbally, but we'll quantify it when we're trying to analyze how this is a function of temperature and pressure and such. So what you do is you get this third body colliding partner. Then what happens is you form a excited or some transition state after that collision. So these collide together. This causes a change in this species. It's similar to what it started off with, except some different state that results from this collision. Then nothing happens to this one. So what's happening is you have an energized this collision gave it a boost. Energized species. That's what this asterisk is. And then this third body it's the collision partner which gave it some energy. So due to this collision, either this partner gave it some energy due to its kinetic energy, or it just activated the right spot on this molecule. It became different, similar but different. So this is all another way of saying this, that this became activated. It's now woke. Okay. Then once you have this activated species, it can form this new product. So that's the product that you see here. It happened after it became activated. So that's basically what happens, is that even though we see in a global summary that it looks like the species just transforms in some single solo process, that's the global description. But if we break it down into how this process works, there's an elementary steps in between, and it involves anything that's in there to collide to make this activated species. And then once it's activated, it can proceed to the rest of the transformation. And then to close, to terminate this process, you could also either form this product, or this activated thing will collide again to deactivate it. So this third body can come in again and say, hey, calm down. It can hit it in the wrong spot and it'll no longer be activated. So the reverse of reaction 1 is also possible, where it collides with the third body, becomes activated, and then the next collision or collision after that once it's activated with the third body would deactivate it, make it less reactive. So here, this is what the products can be a dissociation. It can fall apart. Dissociation. So the activated thing is what gets the reaction going forward. And then here, this is a deactivation by subsequent collisions. Okay. So a couple of other notes is that what we're doing is that A is energized which allows for energy barrier to be crossed. So once you're activated, you have more energy. If there's some certain process that has a barrier, it can be crossed with once you get this activated state. So that's why it seems like it's happening from nowhere. That's the net process, but in between there, you have to form this activated species. Then you can cross this energy barrier. So it's a unimolecular process because that's the only thing that's changing, but you need this collision partner to get energized. And then anytime you have a collisions, oh, this is a no pun intended here. Could be a bullet point, not a activation. Collisions always results in deviation so the mean energy level is closer to this non-activated species. But anytime you have a collision, there's a possibility that something will happen. You'll hit the right spot. Your kinetic energies will combine to make it a faster kinetic energy, some fluctuation away from the mean. And in this case, you went up, and then in this case, you went down. So collisions have to happen for a chemical reaction to proceed. And then once you collide, there's different deviations from the mean that can happen. Okay? So let's start to analyze this stuff. So what we're going to do is use the laws of mass action to keep track of destruction and production of A, and production and destruction of this A star, this activated species. That's going to give us some insight into how to express the rate of reaction for each of these steps and get some insight into the physics of what's happening. So if we were to track A, the activated species, so what is dA dt? And so that expression, the law, we'll use the law of mass action for this mechanism. So A star gets produced in reaction 1 going forward, it gets consumed in reaction 3 going forward, and it gets consumed in the reverse reaction of 1 going forward. So that would look like the rate of accumulation or depletion is based on these three. So the forward step of reaction 1, that depends on A and M. It gets consumed in reaction 2. That only depends on the concentration of the activated species. Then it gets consumed in the reverse. So it participates in all three steps of this mechanism, and sometimes consumed, sometimes produced. Okay? So if we apply the steady state approximation, because this activated species is reactive, so it reacts immediately after it gets produced, and it could either accumulate with time or it can get depleted. So we'll see how this works if there's some accumulation and then some period of accumulation, and then it reaches a steady state where it reaches a concentration but then stays at that same concentration because it gets consumed and produced with some balance. And that depends on the radical and the specific process, specific conditions. But let's see how this analysis looks by applying the steady state approximation. So if we were to say this dA dt would be 0. So that means steady state at steady state. So when you do that, you can say that you can relate these to each other. Okay, that's how the steady state assumption would look. You would say that there's no accumulation or depletion of this activated species. So now we can use this in our analysis of A to see if that helps us to understand what's happening to A. So if we were to track A, the change in concentration with A with time depends on the forward, it gets consumed in the forward reaction. Doesn't participate in the second process, but it gets produced again, it gets replenished if this activated species does not proceed with the other dissociation or other process. So that's how that would look. Then we can plug in this steady state expression to this A star or this M. So what we're going to do is solve here for A star, K2 A star. So if we solve for this A star, plug it in there, what you'll see let's see here, what are we doing? So let's do this. So what's A star steady state? This is steady state. So this would be so it looks like the steady state concentration of A star doing from the laws of mass action for that mechanism is the forward reaction of 1 divided by this. Well, all right. So if we were to plug this into here, the moral of the story is that if we do the algebra, it's actually cancels out to give you this. The steady state concentration of the A star, plugging it back into this law of mass action, shows you that the accumulation or depletion of this initial species A is related to the steady state concentration, applying that. Okay? So let's see, where can I write this? Yeah, I'll just write it down here. So another way to write this is that so this whole thing, similar to what we had here, this is another way to write that. So if we were to say that, okay, this rate of consumption or production is some big effective rate constant, K effective, K effective, okay. So this is the net process, this is the mechanism. And if we did this analysis applying the steady state assumption for this energized radical or energized species, and we showed that you can organize it such that applying the steady state assumption you get this effective rate constant. So I'll write it over here. It's this thing, and I'll write it in a different way. So I rearranged it so that we can for some insight that I'll talk about next. But so this effective K, it's based on K1 forward, K1 reverse, and K2. And it's related to the third body. Okay? So remember, so M is the third body. This is any molecule in the mixture, gas phase mixture. So the concentration of that is N over V total. So all of the molecules in the mixture contribute to this concentration, this density of this concentration, or the density of molecules, moles per liter, moles per volume, in the gas phase. It can be related to the ideal gas equation using N over V. So for the gas phase, we just use this definition. So by this definition, the molar density, this concentration of the third body, is just based on the ideal gas equation. So we can write limits. So this depends on P and T. Let's see. Running out of space here. So if we look at this expression here, we can plug in that this second term there, K1F, it depends on the total pressure in the system. So if, as P goes to 0, this term dominates. So as what happens is that this term gets very, very big at low pressures. This gets very, very big. So this term gets very, very big. So that dominates this effective pressure. So then you get that the effective rate K1 forward at high pressures. Then, in the opposite direction, as P goes to infinity, this goes to 0. This goes to 0, so then you're dominated by the left-hand side. So because there's a pressure dependence with this third body here, if you're at super high pressure, this term of this effective rate dominates. If you go to high pressure, this goes to 0 and then this dominates. So what's happening is this unimolecular process, because there's a third body in there, that third body concentration depends on the ideal gas equation, which has a strong pressure dependence, or like this linear pressure dependence. So the limiting cases for high and low pressure are pretty clear in this analysis. Assuming the steady state, you get this effective rate constant for A, and if you were to plot this with pressure, which is related to the concentration, the effective rate constant has two limiting cases. If you were to say, this is the line for infinity, you would just get K2, K1F, you would have this limit. And if you were at the low pressure limit, you would have this linear function depending on the ideal gas equation. The concentration increases with pressure, so you would have a rate dependent on pressure. So this would be, so that's the linear. So the effective rate constant is the sum of these two limiting cases. At low pressure, it has this linear dependence. At high pressure, it reaches this asymptote. And somewhere in between, it's somewhere in between the two limiting cases. Okay, so from this analysis, when we look at this unimolecular process, what we see is that it depends on a collision partner. Even though this one molecule is the one undergoing a change, it needs a collision partner to get these fluctuations from the mean energy. Some of these fluctuations, some of these collisions will fluctuate it such that you have this energized state, and it's only when you have this energized state can you make this dissociation or make some change to a different species. And so that has to happen. But then another possibility is that when you do have this energized state, it will collide again to bring it back to the mean. And so this is the mechanism for a unimolecular reaction. And if we apply these laws of mass action to the energized species and to the starting species, the energized species, if we assume it's a steady state accumulation, or like it accumulates and then it reaches a steady state concentration, we can get an expression for the concentration of this starting species in terms of the steady state concentration, and that results in this effective lump here. Rearranging the algebra, what we see is that you get an expression like this because there's a third body dependence, because it depends on the collision partners. That number of collisions depends on the number of partners you have, the number density. By the ideal gas equation, the number density depends on the pressure and temperature. So we can write these limiting cases as a function of pressure. At low pressure, this linear trend is how this rate, effective rate happens. This is the most important part. At high pressures, you have this dependence here. So the way that we wrote it, we can see that these two limiting cases apply. At low pressure, you have this linear relationship. At high pressure, you have this limiting asymptote. And in between, it's some combination of those. So that's the dissociation mechanism, or change due to some single species happening. And what we saw, it depends on the collision partners, the third bodies that are happening. So with that, we'll go ahead and end there, and I'll see you guys next time. Thank you.
Okay.
Yes.